All right, let's keep going. All right, so let's look at SQL queries. So SQL queries. So we just went over some of the topics in relational. Where is it? So I wasn't able to cover the whole thing. I like to keep going with SQL queries, but relational algebra basically is the basis of everything else, right? We have that the SQL language is based on those initial ideas, right? That were first thought of in general, regardless of what particular implementation we eventually we did. So certainly SQL is the de facto language that we use for interacting with relational databases, but certainly does not implement the entire set of relational algebra. It was an attempt to creating something was easily readable, something that had a low entry bar, right? That was pseudo English readable, right? But has the following syntax for various operations. So here's the select based on the relational algebra, where you have a select clause of the fields that you want to grab, which kind of brings together both the select and the projection, right? Both were merged into a single statement. That's the select and the fields from which tables you wanted to retrieve, and allows you to, the select allows you to, again, like we saw earlier, a filter across multiple tables into just a subset of the entire data set. Okay, so here's the original data set that we were looking at from last class. The students, the department, the course, just as a refresher that this is still the data set that we're considering. So here's some of the questions that we were trying to answer earlier, right? Let's retrieve the following fields from this data set. Here we're specifying from which data set we're retrieving it, right? Here we're specifying that we're retrieving these fields from this data set, right? Now, if you only need to specify the name of the table if it's ambiguous, right? If you have multiple tables. Here we just have one table, so it's implied that you're retrieving it from that particular table. You can just it's optional. You don't have to specifically use it. Now this particular query has an equivalent in the relational algebra, right? So SQL is an abstraction on top of the relational algebra. So here we're using several renames and projections and whatnot that can then all be condensed into one single select statement, right? In SQL. So it's much more less verbose, right? It condenses it a lot. Again, there's a lot of shortcuts that you can take if we know that we're using a particular table. You can give it a shortcut name, so you don't have to type the entire name of the table, and then use that instead. It's also very useful when you have a table that is joined with itself, right? That you can refer to the same table using two different names, right? As if it were two distinct tables, which we'll see a little later. Also, you can either specify the fields that you want back, or you can specify that you want all of them, right? So you don't have to specify them individual by using the star operator. And if this only one table is not ambiguous from which table you're retrieving the fields, right? You can just drop the table name as well. Here's a couple examples where we are retrieving from two distinct tables, the department table and the employee table, and presumably there's a mapping between the two. The department ID under the department table, you have the ID in the employee, and we are retrieving the name of the name from the employee, but retrieving the department name from the department table. Here, since since name is exclusively in the employee field table and dname is exclusively in the department table, we don't need to prefix the fields with the name of the table, right? But if you had name in both tables, then you would need to prepend it with the name of the table, right? Because otherwise it would be ambiguous. You don't know what field you're retrieving from which table. Do we win? Somebody won something?
There's a sorority thing.
Oh, is that? Okay.
I've got all sorts of lays.
Okay. Here we have, here's an example of using, retrieving all the fields from the person table. Here are all the fields, but if you just want two of the fields, last name and first name, you can explicitly select them in the select clause. If the table has the same value across many rows, you can also use the distinct keyword, right? That will make sure that the same value does not get reported more than once in the results. Types, the fields themselves have a particular type. You can specify the type so that you can ask the database to validate, you know, when you're inserting, when you're updating data for a particular record, to make sure that it validates and it doesn't allow you to insert data, bad data. Okay. Also, the fields you can use all sorts of functional operators that allow you to manipulate the data arithmetically or string operations or date operations, all sorts of operations on it. You can do lower, upper, right, to do some string operations. You can remove extra spaces in between or calculate the length of a string. Everything you would expect in a full-blown programming language. All those operators are there. You can calculate the substring or whether it's contained inside of another string. There's various operators that allow you to retrieve the currently logged in user or concatenate various strings into larger strings, or do some pattern matching if a string is equal to other substrings. So here's an example of using the like operator where you can pattern match a word such as Einstein, see if it pattern matches with underscore I ampersand, where the underscores match a single character, whereas ampersand matches 0 or more characters, right? So for instance, this pattern would match all these strings down below. And so you can use these like patterns in select statements. So you can retrieve certain records that match a particular column name that matches the pattern on the right-hand side. All other wildcards in there, we already saw ampersand and percent and underscore. But you can also list all the characters that match, whether it begins at a line or at the end of a line. And there's a whole syntax. I'm not going to go over all of it. So here's an example on retrieving certain records that have that pattern match on the city. So I want all the folks that whose city start with LO, right? And by default, it's case insensitive, although you can make it also case sensitive as well. There's all sorts of date operations that allow you to retrieve the current date, format it, extract the month, the year, the day, and do all sorts of interval operations where you can add certain number of days, subtract certain number of days, and do all sorts of date operations. You can certainly retrieve the current date or extract certain pieces of a date, and all sorts of date operations where you can add days, remove days, add years, add months, and so on and so forth. Certain vendors have different formattings for different data types. Most of them are consistent with one another. Some of them are very, very proprietary to the vendor. The vendor will try to sell you on several features that are specific to the vendor, to try to lure you into their particular framework, to make it harder, later on to migrate away from a particular vendor. Ideally, you would like to stay within the standard, the SQL standard, and as much as possible to make it easier to migrate to different vendors at a later time. So each vendor might have any number of functions that are specific to different operations. See, here's just a few functions that allow you to retrieve the current date and do all sorts of date arithmetic, being able to add or subtract or calculate the difference between two dates, or format the data in a particular format, international formats. And again, each vendor will have any number of functions that are specific to that particular vendor. So here's a couple of I think this is a SQL Server that allows you to convert from any number of representations. They have their own little codes that allow you to convert between different notations, that are abbreviated or expanded to contain full month names, year or day names, or have military or European or have American standards formats. All right, so let's go back and look at the syntax of the select clause. Here's a little more on the fields that can be retrieved. S being the table, the student table that we're referring to here, and we're saying s.star, meaning I want all the fields in the student table. Plus, I like to create a couple of on-the-fly fields that were not there in the original in the original table, which is the extend. Right, it's the extend feature that we saw in relational algebra. Here we are creating a brand new field that is calculated on the fly, that subtracts the graduation year minus the year that the college was founded, and it creates a brand new column called graduation class. It also renames the one of the fields, BC as college, right? So again, it allows you to extend and create brand new fields. So there it is, the result set. So here's an example on how would you start off. So here's a select that retrieves only those three fields that already exist in the student table, but we can do some transformations, right, to convert them into another representation where we might rename the field that in the student ID as newest SID, right? And we can rename the graduation year field to graduation decade, right? And then add additional transformations where we can concatenate a student number, right, in front of the student ID, and then the resulting concatenated string, right, put it under a new field called new SID, right? And further do some additional calculation where we can divide the graduation year by 10, cast it into as an integer, and then multiply by 10, right, to get rid of the decimal points, right? And then convert that and put it under a brand new column called graduation decade. Right, so here's a combination of doing numerical conversion, casting, and a string manipulation, all in one single select statement. And here's what would be the resulting query. Okay? And this certainly could be an input, right, to an outer query. You can also do on-the-fly calculations based on logic. Right? As I am iterating over all the records, I can use those values in statements that are logical statements that can compare things that are equal or greater than or less than, and match them against multiple cases, right? So this is very similar to a switch case statement where you have a condition that gets compared to multiple possibilities, and then the ones that matches tells me what the resulting value for that particular column is. So here we have an input value, right, of this table A 1, 2, 3, and here we have a simple transformation that checks the value of A and compares it against multiple possibilities. If it's 1, then the value of the resulting field, new field, is the literal 1. If it's the number 2, then it's the literal 2, and so on and so forth. Now notice that this one, we didn't provide the name of the column, right? Whereas this one, it was clear that was the field A, right? Over here we didn't provide it, and what vendors will do is that they'll try to guess or provide a default name for the new field that wasn't there, and typically it'll be based on the operation that you're doing. So it'll use case, or if you have min or max or average, right? If it's an aggregated value, right, it will build a new name for that field. Here it grabbed the name of the operation. The case operation has a optional or an alternative syntax that might be a little bit easier to read, where you have a single expression and then it gets compared against a single value, right? And the one that matches, then it gets evaluated to that then clause. So we can rewrite the previous one to be one single expression that gets compared against several cases, right? They then get evaluated to the literal 1, 2, or other. Here's another one where we are calculating an arithmetic expression, and we are subtracting. We're first extracting the year from the current date, and we are subtracting the graduation year. So we are calculating how far along, how long ago did you graduate, compared to today's date, right? And then we can tell you how many years have you been an alumni of the college, right? So here's where the calculation is done, and then that value gets put under a brand new column, a brand new field called alum years, right? And so the resulting, I don't display it. No, I don't display the resulting table. But nevertheless, here the calculation here, right, that calculates how many years have you been an alumni. Conditionals. So earlier the value in the case that we were using earlier, the name of the field was being selected by default by the vendor. Here we are specifically saying what we want to call the new field, right? So here we have the case and the else statements, and the resulting value is going to be calculated under the graduation status new field, right? So for instance, if the number of years that you've been with us is more than 0 years, and you're an alumni, right? Otherwise, you're not an alumni. You are in school still, right? Here we have a perhaps a little more readable version of this, right? If you have just one single case that you want to elaborate, instead of having multiple case then, you can have a single if statement that can then evaluate the predicate, and then have kind of like an Excel, right? You have the first argument is the predicate, and then depending on true false, right, it evaluates to either the second or third attribute in of the if statement, okay? And then put under the column that you provide as in the as clause. All right, so we looked at the select clause, right? You can then also provide from where are you retrieving this value? What are the data sets that you are retrieving it from? And that's for the from clause. The from clause, you can specify what tables are you drawing your data from. Here we are drawing it from 2 tables, the student and the department. Notice that here, this is the equivalent of the cross multiplication, right? Here we're saying take all the students, right, from the student table, take all the department from the department table, right? And then just combine them all, right? And since we have 3 departments and we have 9 students, it's a very small college, we get all 27 possibilities, right? We have all the students combined with all the, I don't have an example. We would have all the students combined with all the departments. I think we did that in the previous slides, right? We saw how they were all combined. So it grabs, in total you're grabbing in all 6 fields, 4 fields from the student and 2 fields from the department, right? All combined with one another, right? In this case, in this case, there are no fields that overlap, that have the same name under both tables, so we don't have to rename them. Otherwise, we would have to rename the fields, right? So here, if there were fields that have the same name, we would have to make sure that we rename them. Especially, notice that if we are cross multiplying tables, the same table with itself, right? You would have 9. If you have 9 students with 9 students, you have 81 different possibilities, right? Each student combined with all the other 9 students. At the end, you're going to have 81 possibilities. So what will happen is that the student names of one of the tables, right, is going to collide with the same field, right, in the other table, which is really actually the same table. To be able to distinguish, right, where are you grabbing the fields from which table, you can distinguish them by renaming the table, right, which is basically just the rename in the algebra, right, in the relational algebra we saw earlier. That you can just rename the fields to have something different, right? Okay. So this is the cross multiplication, right? In the cross multiplication, you just basically take all possibilities. But as we saw earlier, when we looked at the example in the relational algebra example, we don't want all the possibilities, right? We want to be able to filter and only keep the ones that make sense, right? For that, we introduce the combination of the select, right? That added a predicate, right? That we want to match, and that we called it. It was such a useful operation, right? That we gave it its own name, right? The join operation. So SQL certainly implements that using the join keyword between 2 distinct tables. Same thing. It only takes 2 at a time, and it gives you a predicate that on which you want to filter on, right? Presumably, these 2 fields are somewhat related to one another, and this allows you to filter which ones you want to keep. So here it is. You have different versions, right, of the join depending on what do you want to do with the ones that don't match, right? What about all the records that don't match, right? So certainly you're going to get back all the records from both tables that do match. What do you want to do with the ones that don't match, right? Also, you might want to. You don't really care about the other table. You only want to see which ones of the records on one of the tables match the other, but you don't really care about the data from the second one. You just want to answer the question, which one of these match those? But I just want to know about one of the tables, not the other one, right? So depending on what it is that you want to do in the joins, there are different versions of these joins that specialize on the various use cases of what you want to do. The most common one is just joining on fields that match, right? That's by far the most common use case, right? But certainly there are alternatives of where you want to use the other ones, right? So here's this most common joining, where you are joining, matching fields that have relationships with other fields, is normally referred to as the inner join, right? It's the most common join. So here's an example that you have 2 tables here, the persons tables and the orders tables, and and the orders table has a foreign key that is referring to the persons up here, right? So these ones and threes and 15 presumably have a mapping to the person table up here, right? And so these foreign keys, right, in the orders refer to the primary key and these persons. So if we join them, right, we would be when we join them, we find that that Boone Dan has 2 orders and Charlie also has 2 orders, right? All the other ones, all the other cross multiplication possibilities are filtered out because they have no meaning, right? Because they're not related to one another. But what if you did want to keep track of the records that don't match? Okay, there are certainly records. There's certain folks that don't have any orders, right? Or they might have some orders that don't have any people, right? That don't match. What do you do with the ones that don't match? Do you also want them? Typically, the answer is no. Right? You don't need them because there's no relationship, right? That cross multiplication doesn't matter. So first, let's look at cases where it doesn't make sense first, right? And then we'll see an example of where it does make sense, that you want the data even though, right, they don't have any relationship. So let's look at ones that don't make sense first. So here we have the left join that says, okay, give me all the records that match between table 1 and table 2. Those make sense, yes? They have a relationship. But I also want the records that don't match from the left table, right? Table number 1, right? I know that records in table, there are some records in table 1 that don't have a relationship in table 2, but I want them anyway. Okay, why? It might not make sense. Most of the times it doesn't make sense, right? So here's a couple examples. Let's look at these persons and orders. Certainly, here's an order. Here's an order that has no person. There is no person with an ID 15. Yes? Okay. And let's see. There is and Dole here. Bob Dole here has made no orders. Yes. So there certainly are some records in one that have no match in the other, and the other that doesn't have match on the one. Yes? So let's match first. Let's do a left join. So left join says here that says, well, give me all the records that match, and certainly these four match, right? These are persons that have records. But I know there's a couple of persons that don't have orders. I want them too. I also want them. And there they are. Here's Bob Dole that didn't make any orders. Make sense? And certainly I don't have an order for them. I can go the other way around. I can do a right join. Oh, wait a minute. I thought I had a right join somewhere. Oh, here's my right join. Why do I have it so far away? Here's a right join, right, where I do the same thing, but I go the other way around, right? I do a right join. I know there's some orders that don't have any people, right? I want them too, right? And there they are. I have the order number, but there are no matching people on the other end. But I want them anyway, right? So these two examples, it makes no sense. I don't want. Why am I even asking for those, right? Well, you might want to say, I want the orders that match, right? But because I want a full report where I have certainly the orders that match. But hey, what about all these orders? Why are they hanging around, right? Did anybody close them? Anybody fulfill them? What happened to that order? How did that order made it into there? But here's one particular question, right? That certainly an outer join might help, the left or the right, where I have a staff and a spouse, and says, and there's a matching here that you have a spouse with their own social security number, but it has a foreign key of the staff, right? So this is the spouse of a particular staff member. Yes. So you have all the staff, and you might want to ask. One of the questions might be, find the names of each staff member right, and his or her spouse. If the question ends here, right, then this would be an inner join, right, because I want the staff and their spouse. Okay, but the question might be, if somebody adds the if any, meaning if they are married, they might not be married, so they might not have a spouse, but I want the employee even though they're not married, right? So that might make sense, right? That I want the information regardless of whether they're married or not. If they're married, I want the information, but if not, of their spouse. But it is okay for them not to be married, but I want still the information for their spouse. So that's where you would use an inner join where I also want the records, even though I don't have a match in between these two tables. That makes sense? So this one would return only the ones that are married, whereas a left join, right, would also return the information from the staff, even if they're not married. Make sense? So some questions might need these kinds of additional queries. A full join would just completely return all possible combinations where you might want to need to know all the possible, even the ones that don't match, right? I want to know them as well. So a full join would give you just everything, right? The ones that match first, and then these are all the records that didn't match, right? I want them as well, right? So it would be a very expensive query, to be able to go through all the possible combinations, right? I would get all the records for each one combined with all the ones that don't match as well. All right, so what if you want to be able to specify not just merging? Yes.
So why did we give the condition in the previous query when it gives everything anyway? So
well, because you would first get the ones that match in that order, right?
Oh.
You first get the ones that do match, and then everything else just follows that doesn't match.
Okay.
Yep.
Would there be a flag to say what followed, or it's an implementation specific?
Implementation specific. Yep. In Oracle, you would say like row num, and you would be able to iterate the ones that do match. In other ones, you have to find it yourself using limit or things like that. Yeah. Yes.
Is full join subset of the cross product?
No, it is the cross product. Yep.
What's the use?
Right. No, if you want to be able to retrieve everything, right? Yep. When you have to be able to the one operation that we look at is have only considered two tables at a time, right? But usually you might want to be able to be a normalized table database typically will have spread the data across multiple tables, right? And usually you might find yourself that you have to join two tables, and then whatever result comes after that, you'll need to join it with some other table, right? So to do that, you can use the parentheses notation where you can take them two at a time, right? Where the result of joining two tables, you can then be used to join it with a third table, okay? On a different predicate, okay? Now, if you have several of these tables one after another, the syntax gets fairly hard to read, okay? Where you are just joining on and on and on and on with different tables, so the select statement allows you to specify multiple joins, right? In an alternative syntax, right? The syntax where we are specifying using the normal syntax, right, of using the join keyword, right, and then and then you provide the predicate. You can use what is called the implicit join notation, where you move the predicate instead of specifying it in the join clause, you can specify it in the where clause. Okay, and it certainly becomes easier to read. Right. So let's first look at the where clause before we delve further into that. So the where clause allows you to provide the predicates, right, that are going to filter the cross multiplication across those predicates that are going to need to be true before they get reported in the resulting result set. Okay, so it needs to fulfill the predicate that you specify here. Okay, and the syntax is that a particular column name needs to be operated on a particular value, and if it's true, then it gets included in the result set. Now that operator is used to compare, right? Whether something is equal, not equal, greater, less than, and so on and so forth. Plus, it can be combined with Boolean algebra to make more complex predicates. Okay, so here's an example on filtering on just a single table persons. Only those folks that live in Lowell, right? There's only 2 records there, and we are filtering until we get only 2 of the original 3 records that were there. Now, again, you can combine this to be a little more complex into a use a full-blown Boolean algebra and combine it using parentheses where you can combine several ands and then ors, ands, ors, ands, ors into arbitrarily complex Boolean expressions. So here we are we're comparing, looking for a particular record that meets the criteria that the last and first name needs to be Bob and Dole returns a single record. Or you can here's an example of using or that matches first name column against Bob or Dan, returns 2 records that match that. Or you can combine them both together, right, using parentheses where you can have nested ands and ors. All right, so let's go back to the previous idea that using multiple joins, using the default syntax of the join keyword. If you have just 2 tables, that's fine, right? But if you have 3, 4, 5 tables, the syntax starts to become fairly hard to read. So the where clause allows you to simplify a little bit, where you can use the ors and the ands, right, to create equivalent joining predicates, right? So here we're querying, we're filtering on fields that are not relational, right? These graduation year and names and department names and things like that, right? They don't have references to anything, right? So these are filtering on just non-relational fields, right? Now, when you're filtering on relational fields such as this, right? Right, these are used to implement joins. Here, we're not filtering on just regular non-relational fields. Here, we are using them to filter on fields that are primary keys that refer to, foreign keys that refer to primary keys, right? That these fields are somewhat related to one another. So here's just showing you an example on how much easier to read using the where clause can be compared to an equivalent multiple set of joins, right? Although you can get away with joins if if you're very systematic, you can format it so that it's still readable using joins instead of the where clause. But nevertheless, they can be equivalent. Right. So here's an example that was pointing out the fact that some of the fields will be filtering on relational data, such as student IDs and SIDs, section IDs, and whatnot. Whereas some of them are going to be on predicates that have nothing to do with relationships, right? And you can combine them with each other. Okay. Between it allows you to to compare a field that falls within a particular range, right? Between values, and this could be strings, or this could be, so they can be alphabetical order, right? Or it can be numerical, or also dates as well. So here we're retrieving all the persons whose last name is between alphabetically, right? Between Boone and Garcia. Here we can also use the not operator, right, to give you the inverse of not being in between. You can also use the in keyword that allows you to provide a set of valid values that's going to be compared, a column name against those values. You have to be careful because this in will iterate over the values in the array here, in the collection of values. So because it uses a for loop, right, to iterate over these, right, it can impact it can impact performance. So you have to be careful there. We'll talk about optimization a little later. Here we're iterating over all the records, right, and comparing the last name, right. As we iterate over these, we iterate for Boone to see if we find it in the in clause, right. If it's found, the very first one that is found, it doesn't iterate over the entire set, right. The first one that is found just shortcuts and says that yes, it's true. I found at least one instance of that, and it returns true, returns that one record that met the criteria. Right, so it has additional operators that can do pattern matching, a field against a particular pattern, or extract values from a field, and you can do that in the where clause to filter out records that meet that criteria, or you can use current user to compare the current user that is logged in against a field. So, for instance, I can use this to be able to retrieve all the records that pertain to me. Right? If I log in and I want to know the sections that I'm teaching and the students that the grades for the students that I'm teaching, I can use current user because I'm logged in. I only see the value that is pertinent to me. Constraints allow you to create in tables, allows you to ask the database to validate, making sure that once you're inserting or when you're updating data in the database, to make sure that it matches certain criteria. Certainly, the data types is one of the constraints, right? You constrain the values to be of a particular data type, and it'll validate if it's not the correct data type. It will not allow you to update or insert into the record. But here's a couple of other constraints that says, well, this value is required. I won't allow you to insert into the table unless I have that value, right? So at least I need your last name. At least I need a primary key to uniquely identify you. Also, I can constrain fields that they have to be unique. I might ask that emails have to be unique or usernames have to be unique. Maybe they're not necessarily be primary keys, right? But nevertheless, I can enforce certain things to not be repeatable. So here I'm enforcing that PID is unique, primary key is unique. Now, different vendors have different syntax. In MySQL, the constraints are specified in their own line, whereas in SQL Server or Oracle, they can be specified on the same line of the field. Again, check the syntax for the particular vendor that you are using. You can name your constraints. For instance, you can specify that a particular field is unique, or the combination of two fields is unique. But then you can name it. You can name your constraints. Where most of the cases is you don't need to name your constraints, but if you intend to later on be able to alter that constraints, then certainly you'll need to have a name for it, right? So you can refer to it at a later time. If it doesn't have a name, then you can't refer it. You cannot alter it. Primary keys is if you know that a field is going to be used in a relationship, right, where one record from one table is related somehow to another record or another table, to formally specify that those two records are related to one another, we specify a particular field to be a primary key, meaning somebody is going to refer to this record, right? And you could get away without declaring something to be a primary key, right? And this will work just fine, right? If you know that this username is unique, right? And it refers to a particular person, and that this website was built by a developer whose username matches that record over there, you could go, right, and just by nomenclature or by convention, right, just make sure that this username matches that other username. Yes? But if you want to verify to make sure that indeed if you're removing a user and you have all these websites that are related to that one user, that one developer, you want to make sure that if I remove the developer, that all these websites are not going to be left orphans, right? That it makes no sense, right? That I have all these websites, but I don't have any owner of that website, right? To enlist the help of the database to verify that doesn't happen, that I don't have data that is orphaned, right? We enlist the help from the database by specifying that this is a primary key, right? Don't allow me to have orphan data, right? That if I have data that is related to other data, that you don't allow me to orphan it. We call that maintaining referential integrity, right? That if you have somebody referencing somebody else, right, that the database is verifying that this makes sense, that you're referring to something that actually exists, right, and that thing, if you remove it, is not going to allow you if you have children associated to the parents, right? So primary key allows you to add that constraint for the database to validate that. So again, different vendors specify it differently. By specifying a primary, it automatically implies that field is unique, right? So you don't have to, in addition, specify that it's unique. It is already implied that it is unique. Again, Oracle is specified in a different way. On the other side of the relationship, right, you specify that records refer to other records on the other table. And you use that by using the foreign key keyword, saying that this particular field refers to another field in some other table, right? So you can say that this particular key, PID, refers to a foreign key, to a primary key that lives in a completely different table, right? Again, so that we are enlisting the help of the database to make sure that it maintains referential integrity, right? We could have done this all by convention, and being very methodical and making sure that our code is right? But if by mistake we remove something we shouldn't have removed, right? Or we update the value of a field that we shouldn't have updated, right? The database wouldn't have complained, right? But this allows the database to catch those errors. Again, SQL Server and Oracle have a different syntax. And you can name those constraints and give them, these names do have to be unique, right? Across all tables, right? So you have to make sure that in a typical case is that you prepend to the constraints, you prepend maybe the tables that are in the relationship to guarantee that they have unique names. You can combine keys, right? The primary keys on a table could be a multi-key primary key. So when you refer to it, you also have to provide the multiple keys. Defaults allow you to define default values, either numerical or string, right? Or retrieve the current date if it's a date field. Now, in the primary keys, oftentimes we provide the primary keys, but oftentimes we want to just delegate that job to the database. It says, you know what, you generate the primary keys for me, right? by either starting at a particular value and then just incrementing from there on. You can configure it to be what's called Auto Increment. Most databases support it. Unfortunately, some do not. And since if you declare a primary key to be auto increment, you can either specify yourself, right, and specify the actual value, or you can just not even specify when you insert the record into the database, and then it will automatically just increment from, just either starting from 1 or the largest number, and then just incrementing 1, 2, 3, 4 from there on. In Oracle, you need to do a little more work here. You need to specify a completely different sequence where you have the values from where the new records are going to read their primary keys from. Okay, just additional a little bit of work. All right, I think I'm going to leave it here. Let me stop this.